Next speaker is Gokce Basar with his last talk on eigenvalue problems and quantization in quantum mechanics. So please
okay.
Yeah.
So do you see my screen and the cursor?
Yeah.
Okay, excellent. So let me give a brief recap of what I discussed yesterday and move on from where I left off. So the basic idea was to construct local solutions of the WKB problem around turning points and patch them, glue them together by the help of Borov symbols, which are defined as quantum actions integrated over various cycles that take place. Basically, they're identified as elements of the homology group of the spectral curve. Right? Borov symbols are resurgent functions of H bar, and they exhibit Stokes phenomena, and all the Stokes automorphisms can be computed through the Delibert-Dillinger-Pham formula, which relates the Stokes automorphism that a Borov symbol feels as it passes a Stokes line to the intersection number of these cycles over the spectral torus. Okay? And if there is a cycle that intersects with multiple other cycles, then they're all they all contribute to the crossing formula. Okay, and we also saw that this gluing procedure can only be done for well-behaved wave functions or whatever boundary conditions that I impose on the wave function, only for certain values of E for given H bar, or if I fix E for given values of H bar. And this was the exact quantization condition, which is also sometimes known as the Voros-Silverstone connection formula, and that was given as a function that these Voros symbols satisfy. And because these quantum actions depend on the energy, this is an implicit function for energy, which in principle can be solved for energy, and that gives the allowed energy levels for. So that's the quantization condition. I wrote out a couple of examples, harmonic oscillator and the double well problem. There's a very nice discussion of these ideas from a slightly different perspective that uses the Wronskians associated with the wave function, and that derives these formulas from a different perspective. For two examples, you can check out these two papers, which I really like. Okay, so let me take off where I left off from yesterday. Now, where I left off was the double well problem, where we have two symmetric wells and a barrier between them. And because the wells are symmetric, we have two cycles. And actually, for any double well, even the wells are not symmetric, it can still be put into the spectral curve is a torus. So they're essentially two independent cycles. I showed the exact quantization takes this form. These two Voros symbols have the following leading order behavior in H bar. So the Voros symbol associated with the with gamma 1 is pure imaginary, and it has the interpretation of the classical action modulo a factor of I plus some quantum corrections. And the other one is exponentially small, exponentially suppressed compared to the to V1. There's a factor of 1/2, and the coefficient is related to the action of the instanton that's associated with tunneling between the two wells, and quantum corrections to that. Okay? And the fact that this power is 1/2 is associated with the fact that tunneling is basically a phenomenon where our particle tunnels from one well to the other. So it's basically that action is half of the quantum action, because the quantum action is defined as a closed curve. So it's tunneling is basically half of it. And that's this one. Very good. So then we can package these actions into the following form. So I expanded the quantum action in h bar. The leading term here is a constant, which is 2/3 in my normalization. This is the instanton action, and all the other terms in h bar can be packaged as some fluctuation function that I denote as f instanton. And then the classical action, I leave it as is. I also show that both the perturbative and the instanton actions, the full quantum actions, are sort of given in terms of hypergeometric functions, and they can be expanded. You can find the formulas in the in yesterday's slides. And we can solve this equation order by order. For instance, if I just ignore the exponentially small part and just expand, just solve e to the I over h bar times s, the perturbative plus 1 = 0, then that just gives the good old Bohr-Sommerfeld quantization. And if I just invert this to find energy as a function of the level number and h bar, that gives that gives me the perturbative expansion around the bottom of the well, around the harmonic oscillator. That's why I call it SPT. And to take into account the exponentially suppressed terms, we can now start with the leading order, ansatz leading order in h bar, and just keep track of the exponentially suppressed terms, but don't worry about the fluctuation, which are power series in h bar. Okay, so once this term is valid, once this term is not neglected, now my energy level is not exactly a half integer, but it's a half integer plus a bit. Because of this term here, and we can expand in for small values of energy, and then solve for the bit. Okay, if we do this in leading order, we find that the leading order term is exponentially suppressed, proportional where the exponent is proportional to the instanton action. So let's now go one more order in e to the minus si over h bar. Okay. Now, in order to do that, I have to expand also the fluctuations in energy. I can do that because this is also a hypergeometric function, which I can expand in E. But this guy has a log term here. Okay. Now I take my ansatz, put it back, solve for epsilon. And because of this log term here, when I plug this E into here, that creates a log of h bar term, like that. And when I plug this back into the equation and solve it to the next order in my exponent, and that creates a log term. Okay, so there is so this log term actually is associated with an event where I have tunneling to the next well and then coming back. Okay, so this is that's why there's a 2 here. It's an instanton anti-instanton event. So here it is. So So of course, instantons, tunneling events contribute to the energy level, and that splits the even and odd states. But let's say for an even state, there are also events where I tunnel and come back. So that shifts the energy level. It's doubly suppressed exponentially because it goes and has to come back. And in terms of Euclidean solutions to the path integral, which I can formulate quantum mechanics in the language of path integral, which takes into account all possible configurations. And one such configuration in Euclidean space, because this is a tunneling event, is where my particle goes from one well to the other, like this. So it goes from x1 to x2. This is the Euclidean time, and then spends some time there and comes back. So this is my anti-instanton. This is the upper part of this trajectory. Okay. So this type of event has to be included in the path integral. Therefore, it shows up in the spectrum. Therefore, it shows up in my energy level expression for the energy level. And this law basically comes from the fact that when I take into account these instanton anti-instanton terms, I have to take into account all possible separations in Euclidean time, because these are all valid solutions. So I have to integrate over this separation between instanton and anti-instanton. And when I do that, I generate a law. Okay, so is the physical interpretation of this law. Okay, so now let me give the sort of the bigger picture. In principle, I can just solve this exact quantization condition order by order and just generate the perturbative series. This is just the Bohr-Sommerfeld quantization, and then take into account the exponentially suppressed terms that generates the instanton part, and then fluctuations around them as well, and then again solving for this epsilon again to higher and higher orders, I can generate terms which are exponentially suppressed, even more suppressed, and each of these integers denotes how many instantons there are. So I might have events that that tunnel from one well to the other, tunnel back, and will go on for forever. Not forever, but some number of times, and they're all here. And of course, for multiple going back and forth terms, I have logs, and of course, each of these terms have perturbative fluctuations in H1. So this is the resurgent, the full resurgent expansion for the energy level for and of course, this expansion is good for levels near the bottom of the well, but in principle, I can work out the exact quantization condition for different different regions in the spectral curve, and then do the same expansion and work out the spectrum at whatever energy level I want. Okay. So one remark is that if I look at these coefficients, I will find that at large orders in the perturbative series, these coefficients diverge factorially, and they diverge in a way that, this is what I call SI notation. It's a little bit inconsistent, but this is just 2/3 the number, the instanton action, right? So they diverge in a way that the instanton action shows up here, and then there's 2 instanton, and so on and so forth. And these coefficients here are related. So the C0s, the 0 here, 0 denotes perturbative, 1 denotes 1 instanton, and so on. The coefficients that enter into the fluctuations, the low order coefficients that enter into these fluctuations, show up in the high order terms in my perturbative series. Likewise, if I look at this fluctuations of instantons, then I will see the coefficients for 2 instantons. Okay. Now, let me move on to a slightly different. Let me consider this problem from a slightly different perspective. Okay? So again, I have the exact quantization condition. The actions are given as integrals over some sort of the classical momentum and some column corrections to it. And once I integrate over the appropriate cycle, they're given as some functions of energy. I also showed yesterday for the double well that all the higher order actions that show up in these series, these are functions of energy, are actually related to the lowest order action, S0, in a fairly simple way. So they are linear combinations of S0, and the first derivative of S0 is a function of energy, multiplied with some rational functions of E. And these rational functions are also special that they only have singularities at the locations where the original spectral curve has singularities. Namely E equals 0, I think in my normalization 1, 8, and infinity. And no other further singularities appear here. Okay, so let me just explain why this is the case, because this is a rather powerful statement which relates these higher order actions to lower order ones in a fairly straightforward way. And furthermore, these coefficients don't depend on the cycles. So all I need to know, if I know, for instance, these functions, all I need to know to go from perturbative, let's say, to non-perturbative physics is just the leading order non-perturbative action. Right, so I'll try to explain why this is the case and how general is this. Okay, so in order to do that, I will set up the stage in terms of a geometric construction. Okay, now this is one of the things that I avoid like the plague, but sometimes I have to do it, which is to change conventions in the middle of the talk. But for this case, I think it's actually useful to do so. So my potential is slightly different than what I used. What I previously had was 1/8 times x squared minus 1 squared, and the reason was that the bottom of the well has this oscillation frequency, which was equal to 1, like the harmonic oscillator, so that I could compare with the harmonic oscillator. But this case for this discussion is a little better, so I apologize for that. But yeah, anyway. Okay, but for this potential, the classical periods. So I'm gonna now talk about periods. So they are derivatives of action with respect to energy, are fairly simple hypergeometric functions. So this is the well, and this is the barrier. Okay, and you see they're the same function except for the argument of omega 1 is E. Our argument of omega 2 is 1 minus E. There's an I because one of them is over the barrier, the other one is under the barrier. And there's a strange mismatch of the denominators, and it's not a typo, and that's sort of going to play some role in the discussion. Okay. Now, these two periods are actually correspond to the to periods on the spectral torus, omega 1 and omega 2. the two independent periods of the torus. And I can define a modular parameter, which is the ratio of these periods, but with a factor of 2, which again is going to play a role. And this 2 is actually related to this mismatch. Okay. Now, these two periods satisfy a differential equation, which is given here. This differential equation basically determines sort of how the shape of this torus depends on my moduli space parameter, which is E. As I change E, the torus gets distorted and so on. And it's all encoded in the Picard-Fuchs equation. Okay, yeah, this is what I said. And the actions, not the periods. So the periods in general for any genus 1 spectral curve satisfy a second order equation, but the actions, because the actions are derivatives, sorry, the periods are derivative of the actions, so the actions satisfy in general a third order equation. Okay. However, it turns out for double well, the actions, not the periods, but the actions satisfy also a second order equation. And the reason for that is these two terms actually can be integrated. So this is a total derivative. Okay, and then the periods satisfy a second order equation as well. And I will also call this equation a Picard-Fuchs equation. Okay, and the two actions are two independent solutions of this Picard-Fuchs equation. And because there are two independent solutions of a second order equation, they satisfy a condition where the Wronskian is a constant. And the Wronskian is given in this nice form. So the action of gamma 1 times the period of associated with gamma 2 minus the other way around. And this is equal to a constant. And this constant can be easily worked out. Because this is independent of E, I can just take E equals 0, and when E equals 0, S this term vanishes because at the bottom of the well the turning points coalesce, so the classical action is 0, and the instanton action is just so the S gamma 2 of equals 0 is the instanton action, so it's the period that connects the two wells, and the periods at equals 0 is actually the period of the oscillation around the minimum of the barrier, the harmonic minimum, and that number. It's a fixed number that can be worked out. I didn't work out here, but it's basically the 2 times it's times 2 because the action is a closed loop. So 2 times the instanton action times the period, okay, times I. This relation has many faces. For instance, it can also be shown because these are integrals over 2 independent cycles of the torus. It can be repackaged as a type of flux over the whole torus, which is a constant, and this can be worked out through simple differential geometry, and this is called the Riemann bilinear identity. So this has a geometric meaning. That particular flux that this quantity is measuring is a constant. And there is a relation to the Seiberg-Witten theory. I won't go into the details of that, but this basically is associated with some renormalization flow in Seiberg-Witten theory called the Mottone relation. Okay? So it's a rather famous equation. All right, now let me just give the general statement. I won't go into the full proof, but just say it in words. And this is true for any spectral curve that is genus 1. Okay. So the actions are can be expressed as elliptic integrals that take value on the homology group with the 2 cycles. So the integrands of the higher order actions can be generated recursively from the square root of q. This is the first term in the Riccati, and if you use the recursion relation of the Riccati, the higher order actions will have some powers of square root of q in the denominator, but there will be no additional weird singularities that the original spectral curve doesn't have. Because they're elliptic integrals, they must be given a combination as a combination of 3 independent elliptic integrals. There's elliptic k, elliptic e, and there's a pi function. And these 3 functions are closed in the sense that they're closed under differentiation. If you differentiate one, you get some combination of the other, or some combination of the 3 of them. And this is a classic theorem by Weierstrass. Therefore, if you just start from the recursion relation, write the higher order actions and integrate that over these cycles, what you will find is that the nth order term is given can be obtained from the lowest order term that, with some nth order differential operator acting on them. But because these elliptic integrals are closed under differentiation, and the actions, the lowest order actions satisfy a Picard-Fuchs equation, which is in general third order, all these differential, the effect of this nth order differential operator can be repackaged into this form by using the Picard-Fuchs equation multiple times to eliminate higher order derivative terms here. So it will be in general a combination of, the right hand side, these are zeros. So n is gamma of 0. So the lowest order action, the derivative, the first derivative, and the second derivative of the lowest order action with some coefficients which are rational functions of e. So you can automate this in Mathematica. These are fairly easy to generate for any given genus 1 potential, and this is true for any genus 1 potential. However, for double val, as I said, the Picard-Fuchs equation for the action is not third order, but second order. Therefore, we can eliminate further this term because S double prime is proportional to S. And my higher order actions are all related to, again, this is not n, this is 0, the lowest order classical action and its derivative. And again, this equation is true for any genus 1 potential. This is true for certain genus 1 potentials. Double val is one example. So I will move on to which ones. Okay, there are some questions. Sorry, I just saw them. For the first point, when we consider a high energy region, instant on trajectory becomes 2 complex turning points. That's an excellent question. I will give an example later on, explicitly work out that. There's another question that says, in the derivation of the large order relations, I know one uses a Cauchy integral. The non-perturbative factor of exponential e to the minus s over h bar is important because that's how the gamma function comes into the large order relations. Now you mentioned that logarithmic goes around 2 instanton. Yes, right. So these log terms that come from those quasi-zero mode integrals, their coefficients are somewhat. So I also skipped over the Stokes jumps as well. So when we compute these log terms below and above argument of h bar equals 0 plus minus I epsilon, then also we pick up some phase factors and so on. And when that also gives some constraint on how the low order terms of coefficients of h bar are related to the higher order terms that involve log. So you can see that these log terms are sort of, when you go to higher order, sort of reshuffle within themselves. And it fits out very nicely. So Gerald and Mitaten worked this out in the uniform WKB paper. It's it all fits together. All right. So let me move on. Now there is a symmetry in this problem, which is that the oscillations at the bottom of the well here are related to oscillations of the the inverted barrier up to some factor, but this symmetry is present in these expressions for the periods, which is you can see that if you take e to 1 minus e, these two reshuffle within each other with some coefficients, and this e to 1 minus e is actually a modular symmetry of this underlying elliptic curve, which is known as the S transformation that sort of squeezes the torus in one way, like this. And you see that when I take e to 1 minus e, because of this mismatch, there is a factor of 2. So the modular parameter goes to minus 1 over 2 times itself. So this is the S transformation. And if you're familiar with modular transformations, there's also T transformation, which takes T to T plus 1. That's the modular group. And this is a more mundane transformation, which just if I were to invert this relation and write E as a function of tau and all these actions as a function of tau, when I take T to T minus 1, they are invariant. Okay, well, yeah, so if I use tau as my parameter instead of, or moduli space parameter instead of E, then I notice that the periods are actually modular forms, meaning that when I take under S, they transform with a power of tau appearing here, and this is the same equation that I just showed in the previous slide. It's just the squeezing of the torus, and under T they don't change. But the actions, so the actions are not modular forms, but they're quasi-modular forms, and what that means is that when I apply this transformation, S transformation, it goes to let's say S of gamma 1 goes to itself with a factor of tau, which is what modular forms do, but there's a bit. And this bit involves the period and some constant. And this constant actually is exactly the same constant as that shows up in the bilinear identity or the Wronskian or the Mottone relation, you name it. And this is exactly the same relation, actually. So it's just a different way to derive that relation. Okay. All right, so the modular transformations relate the perturbative and non-perturbative cycles, if you wish, or the periods, actions. Now one might ask, okay, but this is just a classical story. What happens if I promote all these actions and periods and so on to quantum actions? Okay, so what happens is actually quite remarkable. It is modified in a fairly simple way. It just happens that there are only two new terms that are associated with H bar, which involves derivatives with respect to H bar, and the rest is the same. I just here just erase the subscript 0 and consider the full quantum actions, and the only changes are these two terms, and the right-hand side is still the same constant. Doesn't depend on H bar. So when I consider the quantum fluctuations, the flux doesn't change the classic in some sense on the right-hand side, but the left-hand side picks up these terms. So a couple of remarks here. This is true all orders in H bar. This is an exact relation. This is valid everywhere in the spectrum, not just for small e, for any e. And this relates perturbative and non-perturbative expansions, because recall that the action associated with gamma 1 is related to the Bohr-Sommerfeld quantization, which generates the perturbative expansion around the bottom of the well, and the action and the period associated with gamma 2 are the instanton ones, and these create the fluctuations, the exponent and the fluctuations of the exponentially around the exponentially small term, and they're related in a fairly sort of simple relation. So in this particular context, it actually turns out that P equals MP, so perturbative equals non-perturbative, in the sense that if I know the perturbative fluctuations, if you give me 5 terms, let's say, in the perturbative expansion, I can generate you 5 terms around the fluctuations of in the fluctuation expansion around an instanton and so on and so forth. So this is in addition to the resurgent relation that relates large order terms and the perturbative series of to the low order terms in the non-perturbative sectors. Okay, this is a different relation. Okay, again, this relation shows up in many different contexts. In the context of quantum field theory, this shows up in the in Seiberg-Witten theory, but H bar in that context is a particular deformation of the Seiberg-Witten theory called omega deformation, introduced by Nekrasov and Chatashvili. And when you make that deformation now, you break certain symmetries in the Seiberg-Witten theory. So the low energy effective theory of that deformed theory is some two-dimensional quantum field theory, and the spectrum here is related to the spectrum of that two-dimensional supersymmetric field theory. And this is again the Matone relation, which is the renormalization group equation, renormalization flow of that deformed theory. And when H bar goes to 0, you get back the Seiberg-Witten theory. And it's also related, again, to a particular integrable hierarchy called the Witten hierarchy. And also it shows up in string theory as well as the holomorphic anomaly equations. Also, I recommend these papers if you want to learn more about the different reincarnations of this equals MP relation. All right. So now one might ask, how general is this? So let me introduce a class of potentials which are given by the square of mth Chebyshev polynomial, where I will consider m as a half integer. So this family of potentials have m wells. So m equals 2 is the double well, m equals 3 has 3 wells, m equals 3 halves is the cubic oscillator, m equals 5 half is the quintic oscillator, and so on and so forth. Okay? M equals 5 is 5 vowels, and so on. Now, this might seem like there are many vowels and barriers, so that we have all these cycles. But it turns out for this class of potentials, all these cycles, or the periods around all these cycles are related, just by some coefficient. Okay, so there are actually two independent cycles. I will call gamma 1 and gamma 2, and I'll normalize so that the gamma 1 is the one that's around the outermost well, and gamma 2 is the one next to it, the barrier. Okay, and all these are related with some factors. Okay, now I can generalize my double well expression, so it's again a hypergeometric function that now depends on M and E in a simple way. Again, the actions satisfy a second order, not a third order, but a second order Picard-Fuchs equation. And there's the bilinear identity, which is equal to the instanton action times the period, which in this case, has some simple M dependence like this. Okay, so now one might ask, okay, does it generalize to the quantum level? Because the modification of this bilinear identity for double well is fairly simple. Is that the case? Well, the answer is no. Well, not obviously, actually. So the bilinear identity, as I show it, survives only for 4 cases. M equals 3 halves, M equals 3, M equals 2, the double well, and M equals infinity, which has infinitely many wells, which is actually the periodic potential. Okay. So there is a refinement of this statement that recently came out. They consider some deformation of the elliptic, the spectral curve, and so on. But I won't go into that. So the simple generalization is valid for only these 4 cases. And there's a very nice geometric interpretation of this. So if I look at this modular symmetry that squeezes my torus, the E goes to minus E. Again, all these functions have some symmetry, so that for all these functions, the top of the barrier is at 1, and the bottom of the wells are at E equals 0. So there's this E to 1 minus E symmetry, which is associated with S symmetry of the modular group. However, that S transformation takes tau to 1 minus tau minus 1 minus tau 1 over tau with some factor R, and T again is more mundane. But this R given here is only integer for the this R is integer only for those 4 cases that I showed, and only when R is an integer, this group, which is known as the Hecke group, has an interpretation as a modular group, which is basically the congruent subgroup of the modular group. Okay, only when R is an integer. And these are the 4 cases. This is the cubic oscillator, double well, triple well, and the trigonometric potential. Now, very interestingly, these 4 cases were studied by Ramanujan many years ago, even before WKB and everything. And this is from his books, collection of his books. Here he has 4 examples. Here what he expands is what I call e to the I pi times the ratio of the periods, or which are these hypergeometric functions, right? What he calls x is what I call E, the energy level, and he considers these expansions and so on. This was his way of generalizing the standard elliptic functions. Okay. And they're known as Ramanujan's elliptic functions in alternative basis. And actually, in this book, there is a note by the editor that says, We do not know Ramanujan's intentions in giving examples 1 and 4, but now it's clear that obviously he was thinking about exact quantization in modular groups. Anyway, so now let me move on to a slightly different example. This is m equals infinity. So this is called the Mathieu equation. And I will answer the first question about what happens when the turning points are complex. This is actually quite interesting. Okay. Again, now we have two cycles, gamma 1 and gamma 2. Again, for e less than 1, gamma 1 is the well period and gamma 2 is the barrier. I can impose block boundary conditions so that when I go 1 period, the wave function picks up a phase, theta. So I left it as an exercise to show that even though it looks like there are infinitely many cycles, because there are infinitely many wells, because there it's a periodic function, actually the spectral curve can be put into a genus 1 elliptic curve by some appropriate change of variables for the momentum coordinate. Okay. Now, so I won't give all the details about it, but the perturbative non-perturbative relation holds in exactly the form that I showed, and the right-hand side is now in these normalizations is 8 pi I, the instant on action times the period of the oscillations. All right. And I can repeat the same game and calculate the energy levels and relate perturbative and non-perturbative expansions and so on and so forth. But let me cut to the chase and just show you what the exact spectrum is. Okay, so this is how it looks like. Now there are different regions in this spectrum, and there is a natural parameter, which is the level number times h bar. Where I can make expansions where this is if the quantity is small or large. This is like a tooth coupling, so to speak, in sort of analogous to tooth coupling in gauge theory. Here you can physically understand that when an h bar is very small, I'm basically at the bottom of the well. Okay, so I have some harmonic oscillator, so the energy looks like this. The square root of 2 is the normalization, so that the period of the oscillation, because if I expand around the bottom, the function goes as x squared. So that's the not 1 over x squared like the harmonic oscillator. So this is that 2, and the harmonic oscillator spectrum times, plus some corrections to my harmonic motion. But because of the block boundary conditions, I have not just even and odd states, but anything in between. And remember from the double well, what happened was, so there was a perturbative spectrum which was degenerate, but when we took into account the exponentially suppressed terms that broke that degeneracy between even and odd states, and led to the splitting. So the same thing happens here. It splits between even and odd states, but anything in between is also, a valid state, which is parameterized by theta here. So that's the band, because it's a periodic pattern. Okay? And the bandwidth is given in this region as this exponentially small term. And the way to read this is, so this is energy as a function of n and h bar. So here in V coupling, I have lines which correspond to different slopes here. These lines are not exactly lines because they are they depend on they acquire corrections in h bar, and they are actually not lines, a set of lines, but they're sort of small bands here, okay, whose widths are given there. When at the top of the barrier, now all the bands and the gaps, or the gaps are the distance between the bands, are of the same order. And when I go high up in the spectrum, now it's has this symmetric almost form where I have very small gaps. Okay, that's what I will consider. So very high up in the spectrum. So the leading order term, I'm going to speed up a little bit. So the leading order term, very high up in the spectrum, I could completely ignore the potential when E is very large, and I just have the kinetic term, which is the dominant term here. Okay, so I have a free particle, but to my free particle, I have some perturbative corrections that come from the potential. And this expansion actually turns out to be in 1 over h bar to the 4, where h bar times mu is much larger than 1. This is actually a convergent expansion. It looks like here, it's an expansion of 1 over h bar to the 4 with some coefficients that depend on mu. And I can follow the Bohr-Sommerfeld type quantization where mu is an integer. This is called, again, in the language of gauge theory, a type A quantization. Actually, I think it was Nekrasov with Witten that discussed this, but anyway. So where nu is the 2 pi times n, it's an integer, so it's like the even and odd states. But if you look at this expansion and take mu as to be an integer, you see that you will hit poles at some point. So that if you look at the denominators, if I go higher and higher orders in 1 over h bar, I generate more and more terms like this here. At some point, I'll hit a pole for, even though it's large, it's an expansion large n. At some point, for any fixed integer n, at some point, this series will blow up because I hit a pole. Okay, and the physics is what happens here is the following. So this expansion, what I call perturbative expansion that has poles, actually describes the location of the center of the gap. Okay, so in the spectrum, so I just took this part of the spectrum. If I zoom in here, I have like very tiny gaps here. So it's not like a free particle where my spectrum is continuous. I have little gaps, and I have a splitting between even and odd states, and this expansion now gives me the center of the gap. Okay. And in this regime, NH bar is much larger than 1. You can check the digital library of mathematical functions, go to the Mathieu functions, and find this expression for the splitting of the even and odd levels here. And in this regime, it's actually exponentially suppressed. Okay. Now you say, okay, so there's an exponentially small splitting between an even and odd states. It's missed by this Bohr-Sommerfeld quantization. This really sounds like instantons, right? And indeed, it is. But now, if high up in the spectrum, the turning points are complex, right? So this is the complex X-plane. My gamma 1 is between minus pi and pi. But now, the other cycle is between complex turning points, but I know what it is. It's some hypergeometric function, and again I can play the same game and find an expression for the level splitting, which is given by some factor. This is sort of the density of states, and an exponentially small term, which is given 1 over 2 h bar. Times the sort of the imaginary part of the cycle. Well, I think in this normalization, in this definition, it's already imaginary. And again, I can expand this for large E, and there's a log and a square root of E. And when I do that, well, I find this exponentially small piece, which exactly matches this expression for my gap splitting. All right. So yes, the exponentially small gap is due to instantons, just like the exponentially small band in the other part of the spectrum are also due to instantons, but these instantons have actions which are proportional to log of h bar, therefore their contribution to the spectrum are given as powers in h bar. So again, my full expression has some perturbative expansion here and splitting terms here, which are due to one instanton and so on. And the bilinear identity can be used to relate the perturbative and non-perturbative sectors here. It's a little bit more complicated. Okay, I am almost done. Because the powers of H bar sort of mix. And finally, there is a very nice quantum field theory interpretation. These complex instantons also show up in pair production problem in quantum field theory, and there's a very nice analogy between different limits that's related to, that's analogous to splitting of bands and splitting of gaps, but I will skip all these. And I would like to thank all the attendees and the organizers for this wonderful workshop. Thank you so much.
Okay, thank you, Gokce, for this really beautiful talk. I mean, these are some quite spectacular and deep cases of parametric resurgence. And yeah, it's extremely interesting. But there are
yes,
a number of questions here. They have priority.
Arkady, it looks like rescaling of H bar. Do you mean the what did I do? Sorry. Doing these this type of relation. Well, if this is what you mean, it is because it actually comes from this RG equation, where from the field theory perspective, H bar is actually dimension-full. It's like a electric field, like in the omega deformation. So it has some scale, and when you do RG, the fact that it's a dimension-full parameter shows up in the RG equation. So it's like in this case, this can be interpreted as some rescaling, if that is what you mean. So I suppose one would like to study a third order Schrödinger-like equation which appears in this hydrogen. Yes, so there is actually, I haven't discussed this, but there in the book by Takei and Kawai, and actually many other sources as well, they do generalize this to higher order differential equations, and especially the literature on mirror curves and so on involve these types of higher differential equations, higher order differential equations. But the analysis is very simple. I can send you some references if you reach out to me by email. And is there anything in chat? Okay.
There is a question about higher dimensional systems during the question and answers.
Higher dimensional system. Not as far as I know. No, there is a generalization for multi-particle systems like Toda chains and so on, where each coordinate corresponds to the location of the particle and so on. That was actually the that's in the original paper by Nekrasov and Chetashvili, and there or actually the ODE integrable system correspondence as well. So yeah, there is a generalization to sort of periodic Taylor chain and so on, that kind of stuff. Yeah. So in that sense.
There are some raised hands, so maybe there is a bit of time for quick questions. Let's see. Yeah. Let me try to allow you to talk. Okay.
Can you hear me now?
Yeah.
Yes.
Good. I find it frustrating that I can't see the people who are asking the questions, and I can't read. Anyway, it's with the double well, as the energy that you're increasing, that you're considering increases through the top of the barrier. Of course, there's a qualitative change from the 2 cycles to the 3 cycles to the 1. Now, associated with that is quite a complicated change in the Stokes constant. It involves the imaginary part of involves the argument of a gamma function of complex argument, when the 2 turning points on either side of the barrier get closer together on a scale of h bar. Now, that's been known since the 1950s in lowest order, but has it been systematically included in the resurgence analysis of the double well, where all the corrections are taken into account?
Yes. So in the review article by Delabere and Pham, they actually they have an example where they work out exactly how that transition happens at the top of the barrier, and they show that these gamma functions show up in as solutions to the Stokes automorphism equation and so on. And I think also Andre's paper, I think the return of the particle oscillator, has an appendix where he works out by cost functions how these gamma functions appear and so on.
Good, because it wasn't a part of, you didn't discuss it.
I don't discuss it, but that's yeah.
Okay, thank you very much. Thank you.
Okay, so thank you again. If possible, let's leave the other questions for after the session ends.
Okay.
And go to the next speaker. So thanks again, Gokce.